All right, so we are continuing with Unit 10, Infinite Sequences and Series, and today we are looking at Lesson 8, Taylor Polynomials. Students will be able to construct a Taylor polynomial of any degree and find a series representation. So we already know how to approximate a function by a tangent line. We did this earlier in the course. The equation of a tangent line is called a first-degree Taylor polynomial. We just didn't call it that at the time. The tangent line approximation at x equals 0 is the first Taylor approximation, which is written f of x is equivalent, or almost, that's what that wavy equal sign is, p sub 1 for polynomial, which is what I've seen a lot of times, which is the function at 0 plus the first derivative at 0 times x. Really, this is y equals mx plus b. It's really y equals mx plus b. And we did a lot of this before. We took, I don't know if you remember, we said y minus y1 is equal to m times x minus x1. And we added the y1 to the other side when we were doing some of our linear approximations. So maybe any of those things look familiar to you. But to get a better approximation, we need a higher degree polynomial. And so we have a formula for that, and that's our Taylor polynomial, which is all listed here. It looks kind of crazy, but the cool thing is it works with this formula where every term is the same thing. So it's the derivative. I'm going to start with the second one. The derivative, x to whatever that same number is over that same number factorial. So second derivative, x squared over 2 factorial. Here it is with my n notation. Taylor polynomials centered at 0 are also referred to as Maclaurin polynomials. Now, I'm going to show you what this looks like before we actually jump in. So we are looking at cosine of 6. So I'm going to switch over here to Desmos. So here's my Desmos. Ignore all this crazy. All right, so what I have for you is the cosine curve. So there's cosine. What we can do is approximate it with a polynomial, and actually 1 is a polynomial. But before, whoops, we were calling this our linear approximation. Hold that thought. I wanted that to be square again, but hey, I stretched it out. So there is, well, that works. The black curve is cosine and that purple line is 1. So we have our approximation. I gotta fix that. My linear approximation. There we go. Now it's looking like cosine again. Hold on. I'm sorry. I gotta fix my graph. I'll be right back. All right, we're in good shape now. My calculator was in degrees, not radians. That's why it was all stretched out. All right, we're back in business now. We are in radians again. So let me close this up here. Now, the line, that purple line, is a good approximation only when I'm near 0, 1. There we go. Only when I'm at that point, 0, 1 is that line a good approximation. So to get a better approximation, we add more terms. So this one has 2 terms, and we would call it a second degree Taylor polynomial. So now if you look at that blue parabola, it's starting to match that cosine curve. It's getting closer and closer and closer. Not too bad. If I add another term, there's 3 terms, 4th degree. So that green curve has even more. And if I zoom out, you'll be able to see. And here we go. Here's 4 terms, and here's 5 terms. So they're kind of crazy. If I turn all these other ones off, that 8th degree, but 5 terms Taylor polynomial, that red one really does start to match cosine. Now, obviously, to get a better match, you would need an infinite number of terms. And so that's what we're looking at today, is all the terms individually, and then we call it a series, and that series represents the infinite number of terms. I think they're pretty cool. They don't have to be centered at 0, but they're nicest to work with when they are at 0. So let's go back to our notes. So here's my Taylor polynomial. Find a Taylor polynomial of degree 6 for f of x equals cosine of x near x equals 0. So 6th degree. So we need something to the 6th power. So we are going to say that f of x equals the cosine of x. And that means if we're going sixth degree, we need 6 derivatives. So I usually organize my work over here on the left to do that. There's no right or wrong. Negative sine of x. The second derivative, so I need the derivative of negative sine would be negative cosine of x. And I'll be right back. All right, sorry about that. The third derivative would be the derivative of negative cosine. So the derivative of cosine is negative sine, but it's already positive, so it's positive sine. The fourth derivative would be cosine. The fifth derivative would be negative sine. And the sixth derivative would be a negative cosine of x. Okay, now we have to evaluate all of these at 0. So the first derivative at 0, cosine of 0 is 1. Negative sine of 0 is 0. Negative cosine of 0 is negative 1. Sine of 0 is 0. Cosine of 0 is positive 1. Negative sine of 0, oops, these should be zeros, of 0 is 0. And the sixth derivative, that's a 0 again, goodness, is a negative 1. All right, so I have that part figured out. Now into my polynomial. So f of x will be approximately my 6th degree Taylor polynomial. So we are going to say f of 0, and f of 0 we figured out is 1, plus the first derivative at 0, which is 0, over x. I like to think of that as a 1 factorial, so not just the formula, but 1 factorial is just 1, so we don't really write it. Plus the second derivative, which is down here, which is a negative 1, x squared over 2 factorial. Plus the third derivative, x cubed over 3 factorial. And the fourth derivative, x to the fourth over 4 factorial. And I'm out of space here. That's okay, we'll keep going. Plus 0x to the fifth over 5 factorial minus x to the sixth over 6 factorial. Now, obviously anything with the 0 drops out, which is pretty great. So this will be 1 minus x squared over 2 factorial plus x to the fourth over 4 factorial minus x to the sixth over 6 factorial. Great. What's a factorial? Sometimes it's nice to have a number in there. Here's p of x. So this would be 1 minus x squared over 2 plus x to the fourth. I have to think about 4 factorial. 4 times 3 is 12, times 2 is 24, minus x to the sixth. 6 times 5 is 30, times 4 is 120, times 3 is 360, 720. I'm pretty sure that's 720. So there we go. That is our 6th degree Taylor polynomial. I don't know, there's something kind of relaxing about writing them all out. It goes by a very specific formula. There are no surprises. No surprises. Example 2, construct a Maclaurin polynomial of degree 7 for f of x equals sine of x. So we're basically running along and doing the same thing here. All right, I apologize for the extended delay there, but we're back. Example 2, construct a Maclaurin polynomial of degree 7 for f of x equals the sine of x. So same process. Let's start out with f of x is the sine of x. The first derivative is cosine. The second derivative is negative sine. The third derivative is negative cosine. The fourth derivative is positive sine. The fifth derivative is cosine. And the sixth derivative is negative sine. And the seventh derivative is negative cosine. Maclaurin, centered at 0. So again, we'll do this at x equals 0 for all of these. Instead of writing out the function notation, I'm just going to write the values. So sine of 0 is 0, cosine of 0 is 1, 0, negative 1, 0, 1, 0, negative 1. So my Taylor polynomial of degree 7 would be 0. Let me think about this. Plus 1x over 1 factorial plus 0x squared over 2 factorial plus, how about minus 1 x cubed over 3 factorial plus 0x to the 4th over 4 factorial plus 1x to the 5th over 5 factorial plus 0x to the 6th over 6 factorial minus 1x to the 7th over 7 factorial. Now, obviously, we've got some zeros in there that we can eliminate. So this is x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial. And when you get rid of those zeros, some even nicer patterns start to emerge. So this is x minus x cubed over 6 plus x to the 5th. 5 times 4 is 20, times 3 is 120, times 2 is 240, minus x to the 7th, 7 factorial. I'm definitely going to cheat on that one. Do you always have to simplify those? I've seen them listed both ways. I've seen them with the factorials. I've seen them multiplied out. It depends. Be prepared to go in either direction. There you go. Maclaurin polynomial of degree 7 for the sine of x. All right, what else do we have? We're not always looking to be centered at 0, and you can apply this concept to any value for these polynomials. And so what we've done here is we've introduced an a. And what this a is, it's a specific value. A equals x1, right? So it's just an x value that we already know what it is. So what you have is this horizontal shift, this x minus a that's in there. And really, you've already looked at this, especially in Algebra 2. You did a lot of it. If you had y equals x minus 2 squared, well, I know that that's a parabola that's shifted right to and opens up. So it's really the same idea. It's really the same idea. So we need to start out with natural log of x. F of x is ln of x. Construct a Taylor polynomial. You know, those little typos that I never managed to fix over the years. Of f of x equals natural log of x near 1. So the first derivative would be 1 over x, which is the same thing as x to the negative 1. The second derivative is negative x to the negative 2. The third derivative is 2x to the negative 3. And the fourth derivative is negative 6x to the negative 4th. Near 1, so if I put 1 in for all of these, the natural log of 1 is 0. 1 over 1 is still 1. Negative 1. 1 to the negative 2 is still 1, but there's a negative in front, negative 1. This is a 2, and this is a negative 6. So my polynomial is going to start out with f of a. So this is the natural log of 1. I know that's going to be 0. We'll come back to that in a second. Plus the first derivative, x minus a. This is kind of over a 1 factorial if you wanted to think of it to the first power. The second one is minus 1 x minus 1 squared over 2 factorial plus 2 x minus 1 to the third over 3 factorial. And I'm out of space, but we'll squeeze it in. Negative 6 x minus 1 to the 4th over 4 factorial. So natural log of 1 is 0. My polynomial is x minus 1 minus x minus 1 squared over 2 factorial plus 2/3. It's not actually 2/3, but it's 2 over 3 factorial. So 3 factorial is 6. So 2 over 6 is 1/3. So this is x minus 1 cubed over 3 and then minus x minus 1 to the 4th. 4 factorial is 4 times 3, which is 12, times 2 is 24, 6 over 4, negative 4, dot, dot, dot. Well, if we only want 4th degree, it doesn't need to go that high. I'm actually going to switch my 2 factorial notation into a 2. 2 factorial is 2 times 1, so that I don't have any factorials in my answer. Okay, awesome. Example 4, find the Taylor expansion for f of x equals x cubed minus 10x squared about x equals 3. So this is a polynomial. Now I'm going to represent it as a Taylor polynomial. The result is kind of interesting, so hang tight, I'll be right back. But the process is the same, even though we have a polynomial. So if f of x is x cubed minus 10x squared plus 6, expansion. Well, we can only go so far for this one. The first derivative is 3x squared minus 20x. The second derivative is 6x minus 20. And the third derivative is 6. And the fourth derivative is 0. That's why it didn't tell us how many terms that we had to have or what the degree was, because we've run out of derivatives. All right, so we want to evaluate this at 3. So this is a 0, this is a 6. 6 times 3 is 180 minus 20 is 160. And now I definitely need my calculator here. 3 squared is 9. 27 minus 20 times 3 gives us a negative 33. And 3 cubed is 27 minus 10 times 9 plus 6 equals negative 57. So what does my polynomial look like? All right, we have the value. So our polynomial is going to be negative 57. I want to go slowly here. Plus minus 33, x minus 3 to the first over 1 factorial, plus 160, x minus 3 squared over 2 factorial, plus 6 times x minus 3 cubed over 3 factorial. I think we got it. Negative 57 minus 33, x minus 3. 160 over 2 would be 80, right? 80, x minus 3 squared. 6 over 3 factorial is really just 1, plus x minus 3 cubed. I kind of like these because you take a polynomial, which it already is, and then you're matching it up with a Taylor polynomial. It kind of looks like a factored version to me. So I think it's kind of cool. Now, obviously, we don't want to keep writing an infinite amount of terms that go on forever and ever and ever. So we need to look at series representations. We want to go back and look at some of those patterns that we found. And this will all start to come together here in a moment. So if f of x equals the cosine of x, and we had said that our polynomial, I'm cheating, I'm coming back up here. I don't have these memorized. Is 1 minus x squared over 2. I believe it's plus x to the 4th. Let's do factorials. 2 factorial, 4 factorial minus x to the 6th over 6 factorial. And then I bet you can see the pattern that keeps going here. So plus x to the 8th over 8 factorial. What would that last term be? That's really what you're looking for here. Well, it would be x to the n over n factorial. Almost. Because it skips every other one and because you're dealing with signs, it's ever so slightly a little bit more complicated, but I'm going to cheat a little bit. This becomes negative 1 to the n, that's the alternating piece, x to the 2n over 2n factorial. So I think you can see the negative 1 to the n because it alternates, but where's that 2n coming from? Well, remember that this is your first term, second term, third term, fourth term. Except we're going to start at 0. We're going to start at 0. Term 0, term 1, term 2, term 3, term 4. So especially on the bottom, that first term is a 2n because it's 2 factorial. So 2 times 1. 2 times 2 gives me 4, 4 factorial. 2 times 3 gives me 6, 6 factorial. So the series is n equals 0. We start with 0 to infinity of -1 to the n x to the 2n over 2n factorial. That is my series representation for cosine. Now for sine, it was just the opposite. If f of x equals sine of x, my polynomial, and again, we already did the work for this, starts out with 0. So we have an x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial plus x to the 6th, nope, not 6th, 9th over 9 factorial. So let's see if we can come up with the same general term. We're definitely going to have to deal with a -1. That's the alternating piece. Let's see if we can label our terms. First, nope, term 0, term 1, term 2, term 3, term 4. So it looks like we're doing 2n plus 1 on each of these, doesn't it? So this would be a 2n plus 1 factorial, x to the 2n plus 1, n equals 0 to infinity. Now, you want to make sure that you get the correct sign. So if I'm on the first term, that should be a negative. If I'm the second term, I want it to be positive. So the second term is 2. -1 squared is a positive. So I think we've got it. So I'm going to look down here and double check. -1 to the n. There it is. -1 to the n, x to the 2n plus 1, and 2n plus 1 factorial. Excellent. All right. Find the series representation for e to the x. We did not do this one. All right, here we go. One more. Find the series representation for e to the x. You want to start out with this whole process again. So f of x is e to the x. What's the first derivative? E to the x. What's the second derivative? E to the x. What's the third derivative? E to the x. Can you see where this is going? Your polynomial representation. And by the way, this is centered at 0. Assume it's centered at 0 unless it tells you otherwise. So at 0, e to the 0 is always 1. So this is 1 plus 1, x to the first over 1 factorial. This is 1x squared over 2 factorial plus 1x cubed over 3 factorial plus 1x to the 4th over 4 factorial. E is actually pretty nice. It lends itself very, very well to these Taylor expansions. Whoops, that's a 5. So I think we can see where this goes. So what would that final term be? Well, there's definitely an x, there's definitely an n, there's definitely an n factorial. You don't have to worry about the alternating signs, which is great. Remember that we're starting with term 0. I'm having a hard time with that. 0, 1, 2, 3, 4, 5, and then things match up beautifully. So what would the series representation be? N equals 0 to infinity, x to the n over n factorial. You might want to just double check a few values to make sure it works. But x to the 0 is 1. You don't have to worry about that 0 factorial idea. That doesn't really exist. So this is legit. It works. But that is your series representation. Now, here is my cheat sheet. Your life will be easier if you have these memorized. There's no other way to put it. I know in this testing environment that we're giving you this year that you are looking up things on your golden ticket and you're looking up things on the series charts that really, really, really needs to be memorized, especially for our paper and pencil test. There is no formula sheet. There is no formula sheet. It doesn't exist. You have one for physics. You have one for statistics. You probably even have one for chemistry. You do not have one for calculus. The ones on the top, I think, are the better ones to work with. We've been talking about this one. Here's your power series, right? We've used that a bit. Sine and cosine, we derived today, and e to the x, we derived today. So I would especially work on those first four. Here's your series notation, and then here's the expanded form. And I know that it's a lot to look at, and it literally does not look like English. And it's not, it's because it's another language. But then this column over here tells you where they converge. So we've been talking about where do they converge and where do they diverge. So look at those, give those a try. It takes some time. It will start to click. It will. These are tricky no matter how you do them, but they will start to click. So please, please, please make sure that you're reaching out to either myself or Mrs. Oakes. We've got one more lesson, and then we're going to start reviewing this stuff. So we're going to get our Unit 10 test in before spring break, so everybody can just breathe over spring break, not do any calculus. And then when we come back, we'll start reviewing. So keep up the good work. I know you're working hard at it.